Hi there, and welcome back to your beloved series, What Can I Do with SQL Window Functions? Okay, we discussed a use case for the lag and lead window functions in the recent video, and this video will be no different. Let's have one more example of the use of, of lag. It is in a completely different setting. The ideas that will pop up are similar to the sessionization problem, but this is a different setting, and seeing the same technique, in this case lag and lead window functions in different settings, I think can be really valuable in developing a sense for when these functions are useful in realistic problem contexts out there. So let's see, what do we have here. This time it's about run length encoding, or in this particular case about the encoding of pixelized or bitmap graphics. Okay, so let's see, this would be the input of our problem. It's a pixelated graphic. You see it's the small letter E in a bitmap form, and we see that you can easily discern the individual pixels of the letter. So this would have 7 times 6, 42 different pixels that make up the letter E. Of course, these darker pixels would be considered set pixels, the lighter pixels would be considered transparent pixels or white pixel background pixels. Okay. There's an obvious method to store such pixelated 2D graphics in tabular form, and that could be the table original. That would be considered the input to the computation that we are trying to perform. As you can see, each of these pixels, each of the 42 pixels would be represented by its individual row, augmented with the x and y coordinates, so that we can easily spot that xy coordinates 1, it's a light or white pixel in the top left corner here, and for x coordinates 7, y coordinates 6, it would be the light pixel in the corner down right below there. Okay, so 42 pixels, 42 rows in table original. That's quite some storage space we are investing here for the storage of this pixelated graphics. So let's try to encode this information in a more compact form. Let's try to compress the bitmap pattern here, and of course compress it in a way so that later we can reproduce it in a faithful fashion. We don't want to have lossy compression or something JPEG style here. We really want to be able to recover each individual pixel after the compression. And one such very simple, super straightforward compression scheme is run length encoding. In run length encoding, we would not view this graphic as a 2D pixel format, but as a 1D sequence or 1D string of pixels. And in this example on the slide, and also in the sample SQL code that I brought with me, we will linearize this 2D picture in walking across it in a row-wise fashion. So we will walk the first row from left to right, and then walk the second row from left to right, the third row from left to right, and so on until we walk through the last row from left to right. So in this linearized form, the top left pixel would be the first pixel, and this bottom right pixel would be the last pixel in the linearized form. If we view this graphic in its linearized form, then we can see that we have streaks of white and black pixels that are adjacent to each other. So white pixel here, but then 5 pixel black, white pixel, black pixel, 5 pixel white, and so on. All right, and we make use of this observation that there are longer streaks, longer sequences of pixels of the same color to only store the color of such a pixel once, and instead remembering how long that sequence would be. Okay, so to save this streak or the sequence of 5 black pixels, we would simply store the fact that we are talking about black pixels for the next 5 entries in the pixel sequence. All right, and this will lead to this entry in the encoded table. All right, so we are talking about black pixels that go on for a sequence of length 5. And this is indeed already the second sequence that we could identify in this bit sequence. Before that is a bit sequence with number 1 of just 1 pixel that's white. And that's, of course, the top left pixel that makes up the first run here. If you follow that through, then you will see that there is only 13 rows in this encoding table. 13 rows in which hopefully many of the sequences that have been encoded are longer than just 1 pixel. All right. So I think the longest sequence here is this sequence of, oh no, it's this black pixel sequence of 7 pixels, I think. Oh, it's even longer. It's 8 pixels. It's 9 pixels. It's a 9 pixel black sequence that we will be able to store on table encoding. And this saves some space. We could even save some more space if we knew that our bitmap graphics is indeed made up of 2 colors like black and white only. Then those pixel colors in the encoded pixel column here would always alternate. They would always switch from white to black, from white to black, black to white, white to black, back and forth, back and forth. So indeed we would not need to store this pixel column at all, because it follows this super regular pattern. Okay, but this is not actually the focus here. It's our focus to implement this arrow, to go from the original regular encoding to the run length encoding here on the right. All right. So how will we do that? Well, of course, we will again use window functions and the lag functionality in this case. So we would first use as input our original table, which is the first 3 columns here, and we would then augment that with 1 more column in which we just write a protocol of whether the pixel color has changed when we perform this row-wise linearized walk through the entire picture. Okay, so let's look at this this pixel. Yep, more focus. Okay, this second entry here in the original table. If we look at its previous pixel, then indeed the color has changed from white to black at this particular point. To document that, we would record this true value here. There has been a change from the previous pixel to this particular pixel. There has been a change. For the next pixel, the third pixel in the table, it's black again, so there has been no change regarding its previous pixel, and we record a false here. And you can see how we would record the true and falses to write a protocol about the borders of the black and white pixel sequences here. All right. Again, much like in the sessionization example, for the first pixel, the first white pixel here, we would always consider it to be changed from, say, an undefined pixel color that is assumed to be the very first, the zeroth pixel of the image, if you will. And we will use an implementation trick that we've already used during sessionization. If you recall, we were using an artificial timestamp of -infinity to implement the fact that each such session log, that in each partition, each session log starts with a new session. Okay, in this case, we would probably do something like this. We would use the lag function to look just 1 pixel behind us, and we would use this particular third parameter of the lag function. If we are at a pixel that has no previous pixel, and that's actually only this particular first pixel here, we would assign its virtual preceding pixel an undefined color, which is of course different from white. So we would record a change of true here and which is what we want, the first pixel is considered to be changed. And from then on, changes are recorded just as you would expect it. Okay, we have recorded true and false change indicators here, change markers. But later on, we will interpret true as 1 and false as 0. And you can probably see where that leads us. A simple sum scan along this change column will then be able to create run identifiers. Okay, this is much the same as the idea of assigning session IDs in the sessionization example. All right, so first, record changes using the lag function. Once you've done that, interpret these booleans as integers 1 and 0, perform a sum scan to assign run identifiers, and this is the final results column that you will then see. This is just a summation of the Boolean interpretation of the change column. Here you see the integer mapping of true to 1 and false to 0. Perform a sum scan and you will end up with run identifiers that correctly identify this run of length 5 of black pixels, for example. All of these have been assigned to run number 2. This is all we need to then derive the final encoding table. I think that's all about the idea. Let's switch over to SQL and see how we can realize that there. All right, so here we go. First, let's create the original input table. I will do that by reading in this ASCII-based representation of this pixelated graphic. As you can see, it's the rendition of the SQL word. Okay, so let's build this input table and then copy the pixelated input there. Okay, we then convert this text-based representation into, this is the text-based representation, there you go, into the original input format that we were expecting using X, Y coordinates and color indicators. All right, so in this case, the colors of this particular picture are very simple. They are either white, like this pixel I've just marked, or they are black, like this pixel I've just marked. Probably you can see it, it's this pixel here. Okay, so these are the two colors that will come up. We also need the undefined color to implement the trick that the very first pixel is considered to be changed in all cases. So what I'm doing here is I'm defining my own enumeration type that can implement these three colors, the white and the black pixel color, as well as the undefined color. All right, so I could go with some integer encoding of colors here, or probably some RGB encodings, but we are talking about text-based pixels here, so I thought this would be appropriate. Okay, so let's create the original table, the table in which we use X, Y coordinates and the pixel color to encode the image. All right, and then from that text-based representation, let's convert that into the XY pixel-based representation. We have seen tricks like this with lateral unness and ordinality stuff before. This is old news. I will just do that here and then show you the original table, and there you go. It has 105 rows. All right, because it has 15 times 7 pixels to store, and here you can see the pixel pattern that has been derived. That would be our input. 105 rows, that's too much. That's too much to store this pixelated representation of SQL. I would be willing to invest half the space maybe. Can we do run length encoding, perform run length encoding on this table to save space? And I think we can. So let's see how run length encoding might look like. We would just follow the plan that we have laid out on the slide before. We would first perform delinearization and then record pixel changes. And this is what's being performed by this simple CTE here. We would scan the original XY coordinate representation of the image, and would then use a window that we shift over this pixelated representation that is defined by this ordering constraint. So first order by y coordinates, then order by x coordinates. This will lead to a row-wise scanning, of the image. All right, so all pixels in a single row would be sorted by this criterion, would be considered equal by this criterion, but inside that single row we would order from left to right. This is just what we wanted. Okay, so the second row would follow next because of this ordering criterion and so on. So this ordering criterion will give us a row-wise linearization of the image. We could easily go by a column-wise linearization by just exchanging these two ordering criteria. Okay, so a row-wise walk across the image. Okay, we would just record the original information that we found at the particular pixel O, but we would also consider the comparison of this current pixel and the pixel just before it in this linearization. All right, if there is no such pixel, we would consider its color to be undefined. If that color has changed from previous pixel to current pixel, then this comparison would evaluate to true, and we would record a change. Otherwise, if the pixel color has not changed, we would require record no change. Change would be set to false. All right, that's about it. That's all there is to it. This is the changes CT. So let's see how that looks like. Changes. Okay, so if we just walk through the table in the middle here, the changes table, then you can see that there is indeed there's indeed been a change from white to black at this particular point. All right, so there's a true here, then there's a streak of these characters, no change color, so we record some falses here. I think this works just fine. Let's scroll to the very beginning of the table, where we look at the very first pixel. Indeed, it's considered to be changed from undefined. Okay, so that would be the change information that's being computed already. Okay, so there's only a second step. There's only one second step actually, and it's about the interpretation of these true and false change indicators as integers that we can then use in a sum scan to assign run identifiers. So a scan over the changes that we've just found. Of course, do that again in the row by row fashion, the old window definition here. Okay, record all the stuff that we've already found, but also use the change indicator, convert it into an integer. So true would be converted to 1, false would be converted to 0. This is very convenient casting that we can use here, and then just do the sum scan in a row-wise fashion. This would leave us with run identifiers. And I think we can see that already. Here are the run identifiers. So these pixels, these 4 pixels of the same color have been identified as run 58. Here's a run of length 1, and there's some runs of length 1, but I hope there's also longer runs. Okay, so a run of 4 pixels again and so on. Maybe the compression ratio for this picture will not particularly great. Okay, so these are the runs. And as you can see, these are still 105 rows. Not much gained yet, but of course, we can now perform the compression through grouping. We don't need this information 4 times in our encoding. We need it 1 time and have to record it that it has been there 4 times. So keep only one of these rows here, but keep a record that it has occurred 4 times. This is run length encoding. Okay, but as I told you already, this is easily done by grouping. Grouping is actually that. It will identify identical runs here based on the run identifier. And this is what you see here. We would just scan the runs table, the table computed below here. We would group by run, so by this rightmost column. All right. I would also group by pixel just so that I can include the pixel in the output here, as you see in the select clause. But will this affect the grouping? No, it won't. Inside any run, the pixel color is identical anyway. So there's a functional dependency, if you will, from this run column to the pixel color column. This will not affect the grouping. We have talked about this already in this lecture. But it will allow me to mention the grouping in the select clause. All right. And here you can see this count is actually very crucial. It's this is run length encoding. This counts the numbers of identical pixels, or the length of the groups actually, and is just the output of our encoding run. Okay, so let's see, encoding. And there you go, 58 rows only. Okay, so that's about half the size. I'm content with that. And as you can see, there is some runs here that I've identified of length 6. Oh, that's not too bad. Some of these are rather short, but well, what can you do? As you can see, and as was expected, the pixel pattern after run length encoding in the pixel column is completely regular, and we could save them spaced there and even get rid of this pixel column here on the right. Okay. So this is encoding, and that's well and good. Of course, we would like to have decoding. So how can we reconstruct? The original image? Has information been lost? Can we recreate the real image in a pixel perfect fashion? And the answer to that is yes, we can. It's the decoding that would need to be done. All right, so let's scroll over the decoding. Oh, as you can see, there is just dots here. I think I recall now. I've removed the decoding step because it's your task to come up with a decoding query. So given the encoding table, reconstruct the original image from the run length encoding bits. And that's perfectly possible. It's a query that you could tackle already. It's really no major deal. Just to prove that this is indeed possible, if you would have created such a decoding table, I think this will be a future assignment, then we could just use this query and convert stuff back into the original image. And there it is again. No pixel lost, everything's fine. All right. So you can look forward to this decoding exercise. Actually, the code is here on the right, but I won't show it to you. All right. So much for lag and lead examples. There is more. There's actually more window functions. So let's enter a new group of window functions with the next video. So we are slowly coming to a close with window function discussion, but there's some stuff left still. You can look forward to that. I'll do. Okay. So for that, see you then. Bye.